for you to look at. And when this happened, they created a very large debris field, which is not a good thing. So with that, the hunt begins. Depending on who you ask, we've got about 16,000 different objects that we catalog in orbit. They're about the size of a softball or bigger right now. There are rumors that there's about 80,000 or so more that are less than the size of a softball that are uncatalogued. As we move further and further trying to solve this problem, we need to figure out how we can predict where these satellites are. This is called the conjunction analysis problem, and how we're going to prevent them from colliding. When they collide, you see they create larger debris fields that sort of act like a nuclear chain reaction. We have more debris, more chances for collisions in space, that kind of thing. This is a very real problem. The green balls you see floating around here are affectionately known as the green eggs of death. They represent the uncertainty we have in the satellite or the object's position, the covariance ellipsoid in technical terms. So this really is a problem for us. We don't know how accurate these satellite ephemeris are. Or I should say, we don't know their positions accurately. We need to know better how accurate they are. And I'll move on to the next one here. We really need to learn how to predict our orbits better. Let's see if this is going to come up. Okay, so once we have these orbit predictions, we can take them and we can run them across each other, and we can say, this satellite, I want to compare your orbit with the rest of the satellites in the globe. I want to know if you're going to cross or there's a probability of collision, that kind of thing. But we really run into an issue of quality, because the ephemeris we use is based off of what's called a two-line element set, or a TLE, and it's only accurate to several kilometers or so. And that's not really good enough to say whether or not you're going to have a collision for sure. So we need better orbit prediction to solve this problem, better data to solve this problem. The owners of these satellites, of course, have better data. The owner of the Iridium constellation, the Iridium Corporation, has very good data for their satellites alone, but they don't have good data on all the rest of the satellites. So logically, you'd think that we could put together sort of a third-party data warehousing group that takes all this good data from all the different satellites into one area, and then compares all that good data against the rest to solve this all-in-all problem. Okay, so we've seen a couple of problems here. Potentially, I got part of the solution here. To better predict orbits, we need to model the forces better, to drive those ellipsoid sizes down, make those green eggs as small as we can. Well, Newton had it easy. He only needed 3 letters of the alphabet to describe how forces are created, but he left the rest of the details up to us. You may recognize the gravitational potential here, and we need all the C's and S's. In fact, we need an infinite number of them to describe the orbits for the equipotential well. This is not easy, but it's something that we need to help solve this problem. One other thing we need, because orbits aren't just a function of the gravitational potential, is atmospheric density data as a function of time. Orbits, especially low Earth orbits, are highly responsive to that. You may notice that the satellites in the videos were traveling around the entire Earth, which makes this an international problem. We need standards across all spacefaring nations who can launch satellites between the reference frames they use, the coordinate transformations they use, and the propagation models they use for these satellites, so that we can then combine all those orbits and do this all-in-all problem. I'm not sure if you're aware of this, but there are no regulations for who can launch into space. There are no regulations for where you can launch in space. You can launch a satellite and put it anywhere you want. The only regulation is on the frequencies, the frequencies you use to communicate with your satellite. So did we find the treasure in this? Have we solved the conjunction problem? We need better data for modeling. We're on the way there. We need a consistent treatment of these low-level routines, these reference frames and coordinate transformations, some more standards, as well as standardized propagation models. So that's it. Thank you.
All right, let's try this. Can you hear me? Okay. I'm Marty Ikehara, NOAA's National Geodetic Survey State Advisor for California. And I'd like to focus on time and crustal motion. Before I joined NGS 10 years ago, I was a groundwater hydrologist with the U.S. Geological Survey in California, and I studied land subsidence. So I was interested in and focused on the movement of the land surface in the vertical direction for most of my career, really. And I think that one of the things that we could use help with in Geodesy is to think about and incorporate more easily the component of time. I liked what Patrick said, actually, is that we think of time as metadata, and I think it'd be a good idea to actually consider time as a critical piece nowadays of data as part of geodetic data. And that relates as well to the movement towards real-time geodesy, which is prevalent in the States and worldwide. It used to be that people, NGS, issued coordinates and they were good for a person's career. And that certainly isn't the case anymore. We have epic dates and we come up with new coordinates by epic date and new adjustments. And time is an important part of that. So being able to incorporate time and to visualize changes in geodesy or geodetic components of the Earth in real time, I think is an asset that maybe ArcGeodesy could be. Most of the geodetic data that I deal with anyway is points, are points. And so we may publish time series of what's going on at a particular continuous GPS station, and you can see what it's done for the past X days or however many years in northern easting and up. But that we're just looking at the time series of a point. We don't have a good way to map that and see what's going on with all 10,000 continuous GPS stations or however many you're interested in looking at on a geographic area. So I think that by incorporating the time component of geodesy somehow and then the geospatial, the mapping aspect of it would be a good thing for ArcGeodesy to try to focus on. Thank you.
Good afternoon. I'm Richard, and I think I bring to the table maybe a rather simple user perspective on some possibly basic functionality that we may want to see. I know that oil company surveyors and geodesists are responsible for some of the largest screw-ups that you'll find, and maybe why we have such a long list of different datums and map projections available in the products that we all use, whether it's Blue Marble or ESRI. And I sort of talked about this with some of the guys in my office that I work with, and we all agree that every time we face a launch of a new computer application or a software version or an operating system on our computers, we've got compatibility issues with data exchange and functions that we may be familiar with, which seem important to us, are suddenly lost, and we depend on quickly being able to find another tool to replace them and to do the job. So I just want to mention a few of the practical computational geodesy tools that my guys tell me that they're looking for, and I know there's crossover with a lot of survey software out there, but everybody will probably share some of these concerns, and some may have been raised already. A coordinate conversion utility of some kind within the ArcMap desktop software with a graphical user interface right off the shelf to help surveyors with some kind of ASCII file import and export, basically to help generate an ESRI data set from point coordinates. So they may have column-based ASCII files and a variety of units and infinite number of datums and